A small workshop makes tables and chairs. It has two limited resources, 8 hours of machine time and 9 hours of labor. How many tables and how many chairs can it produce so that both resources are used exactly? Let's translate this into mathematics. Call x1 the number of tables and x2 the number of chairs. Each table takes 2 machine hours, each chair takes 1, and the total must be 8. Labor gives a second equation, 1 hour per table, 3 per chair, 9 in total. 2 equations, 2 unknowns. This is a system of linear equations. Linear because the unknowns are only multiplied by numbers and added together. No squares, no products of unknowns. Each equation, on its own, has infinitely many solutions. In the plane of x1 and x2, the pairs that satisfy the first equation form a straight line. The second equation gives another line. A solution of the system must satisfy both equations at once, so it must lie on both lines. And there is exactly one such point, 3 tables and 2 chairs. Solving a system means finding where all its equations meet. And keep this picture in mind, 2 lines can also be parallel, or lie on top of each other. We will come back to what that means. Now suppose the workshop adds a third product, bookshelves, and a third resource, finishing. 3 unknowns, 3 equations. The picture moves to 3 dimensions, where each equation is now a plane, and the algebra starts to get heavy. But look at the structure. It is always the same 3 ingredients, the coefficients, the unknowns, and the right-hand side. Let's separate them. The coefficients, including the invisible ones, line up in a table, the matrix A. The unknowns stack into the vector x. And the right-hand side becomes the vector b. We write this as ax equals b. The matrix of coefficients times the vector of unknowns equals the right-hand side. And multiplying the first row of it by x, entry by entry, then adding it all up, recovers exactly the first equation. And this works for any size, m equations, n unknowns. The coefficient aij lives in row I, column j row for the equation, column for the unknown. One compact equation, whatever the size of the problem. This notation is more than shorthand. It turns a whole system into a single object, one we can compute with. The next question is obvious, is there a systematic recipe that solves any system, no matter the size? There is. It is called Gaussian elimination, and it is where we go next.